mountain. I was telling my wife, I don't think I've been here since 2010 or 11, so it's great to see everything. What I'm going to talk to you tonight about is kind of a continuation of that research, actually. But before I start, I wanted to just hear from you a little bit. What is a planet? I want to make sure we're all on the same page before we start out. And even astronomers tend not to always be on the same page with what is a planet. So anyone have a nice definition of what a planet is? You know one when you see one? We're standing on one? Sure.
Something that revolves around a star.
Okay. Something revolves around a star. And that's kind of where astronomers had left it for a really long time, but in 2006, the IAU, the International Astronomical Union, felt that it was actually time to get some formal definition down, because not only had we found a bunch of exoplanets by then, but we had also found a bunch of objects out beyond the orbit of Pluto in our own solar system that made us kind of rethink what might be considered a planet. And this had happened at various times throughout history. When we first found asteroids, we thought those were planets. And so I'm going to put up a slightly easier to read version of the IAU's definition of the planet. And it's basically something that's orbiting the sun, right? It's big and round, and without other big round things next to it. So that's what their definition really boils down to. And you might think, well, then why isn't Pluto still a planet? Because it seems like it fits that definition. But you may not know that Pluto actually has some moons that are about the same size as it. And so do you consider that a little binary planet or whatever? Also, Pluto happens to orbit out of the plane that the rest of the planets orbit in, and it crosses the orbit of Neptune. And we think Neptune's definitely a planet, so if Neptune's a planet and it's cleared its orbit, then what's Pluto doing there? So, we called them, the smaller ones, then dwarf planets, and these bigger ones are planets. But I'm here to talk about exoplanets. Is there a problem with this definition for exoplanets? Yeah, that's a really weird definition, eh? So we just tack the word exo on the front and pretend that it's a whole other class of planets. So planets orbiting a star are exoplanets, a star other than the sun. So I'll start with another question then. How common are exoplanets around other stars? And this is a question that in the early 90s, we still didn't know. And I've got a quote here from a 16th century astronomer, Giordano Bruno, who states, "In space there are countless constellations, suns, and planets. We see only the suns because they give light. The planets remain invisible, for they are small and dark. And there are also numberless Earths circling around their suns." Now, he had no evidence for this at all. It was a hope. It was even in the 1990s, we thought, well, it's possible that there are planets around every star, but it's also possible that we're fairly unique. Right? We had looked for a while and hadn't found anything. But we started to really systematically search for evidence and improved our instruments to the point where today we know of about 5,700 confirmed exoplanets, and this is 5 days old, so there might be a couple more on there, in about 4,300 stellar systems. So that's all since 1995. So in less than 30 years, we've found almost 6,000 planets. In fact, there's plenty more that are unconfirmed. We think that there's probably a planet there, but we haven't got enough information to really confirm it. So that's interesting. and kind of fits with Giordano Bruno's supposition, right, that every planet or every star has a planet since they're so common. But I'm kind of more interested in not just collecting planets. I don't want it just numbers. I'd actually like to know if we can find habitable planets. Maybe, preferably one with friendly intelligence who's willing to talk to me. That would be great. But how many of these do you think you've seen that we've found? Right? Have you seen news articles about Earth-like planets? Maybe finding Earth-like planets? No. So maybe I just read too much news. When I look out at the news, it seems like every other day there's a new article about some astronomer who's found the next Earth-like planet. But the definition of Earth-like then comes into play. And so I would define an Earth-like planet as being rocky, so small-ish, around the size of the Earth, around a sun-like star, so something like our sun, big-ish, but not too big, not too small. And the planet should be in the habitable zone, and this is a term that we use to basically just say that life like here on Earth could form there, and for that it would need liquid water on the surface of this rocky planet. And for that, it can't be too close to the star because then the water would turn to steam and evaporate. Or it can't be too far because then the water turns to ice and isn't liquid. So an Earth-like planet to me has to meet all of these criteria, not any one of them. And a lot of times in the news, if they meet one of those criteria, everyone shouts hooray that we found the next Earth. But in actuality, we found 0 of those. We found 1, right, exactly. We're standing on 1, right? That was the easy one. Typically, we found planets around sun-like stars, but the planets have been very hot, or very close to their star, or very large. Both of those things make them a little easier to find. We've also found some small planets, even some smaller than the Earth, but they're around very small stars. So again, that combination makes them a little easier to find. We've also found planets in the habitable zone of some stars. But they tend to be, again, around small stars, so the habitable zone is also very close, and that means that the planets are typically tidally locked like our moon is, so only one face of the planet ever sees the star. And so, sure, that might be habitable, but it's a very different kind of habitability than we're used to thinking about, right? So we haven't found another Earth yet. But it also turns out that we haven't found another solar system yet. And by solar system, I mean that it's something organized like our solar system that has some rocky planets on the inside, and they're kind of well-spaced, and then there's bigger planets outside, also well-spaced. And so that brings us to a question. Do other solar systems exist, right? Before we found the first planets, we were wondering, do planets outside the solar system exist? And the answer turned out to be a resounding yes. But so far, we haven't found anything that really resembles the solar system. And so before I tackle this, do solar systems like ours exist, I want to bring up 2 other questions that might have a bearing on that. And the first one is just why do we look for exoplanets in the first place? And the second one is how do we look for exoplanets? And both of those things could have an impact on whether or not we'd even expect to see them. So the why, there's many possible reasons, right? We just see them. To colonize them, This one is one that comes up a lot, but it's not actually very practical. Even the closest star to us currently would take us about 1,000 years to reach, and that's only if we turned over the entire economic output of the Earth to building the spacecraft that could take us there, right? I don't think that we can get that organized, actually. And maybe just to know that they're there, right? But I think that the real reason, and if you ask most exoplanet astronomers, and even probably a lot of the people in this room, we'd like to know if we're the only ones out there, right? And so basically the search for exoplanets is the search for life on other planets. I don't really expect to talk to any other aliens in my lifetime, but I do expect that relatively soon, a few decades maybe, we might actually find evidence of life on some other planet than ours, right? This is a question that's fascinated, I think, humanity long before Giordano Bruno even supposed that there were Earths around other suns, right? So one of the things that astronomers and physicists really like to do is they like to know the answer to the question that they're asking before they look for the answer. And that sounds like a contradiction. How can you know the answer before you look for the answer? But basically, we like to kind of get a rough estimate of what the answer will be to make sure that it's even worth asking the question right now. Maybe we're not able to answer that question at the moment. And so back in 1961, Bay Area astronomer Frank Drake wanted to use radio telescopes to look for signs of intelligent life elsewhere in the Milky Way galaxy. And so he decided, before I even look, it would be a good idea to know whether or not there could actually be somebody else out there. And so he put together this equation where N civilizations is the number of communicating civilizations that might exist right now that I could hear with my radio telescope. Our star there is the rate of star formation in the Milky Way galaxy. And we know in 1961, that that's a few stars per year. But for the fraction of planets, the only planets that we knew of were here in the solar system. So we didn't really know the fraction of planets around stars that formed around, the fraction of stars that formed planets. We also didn't know the number of those planets around a single star that would be in the habitable zone. We didn't know the number of those, or the fraction of those, that life could evolve on, and of those that formed life, we didn't know the fraction of those that would be intelligent. Of those intelligent civilizations, we don't know how many would choose to communicate. And finally, we don't know how long that civilization would exist to communicate with. And so astronomers at the time gave their best guesses to all of these numbers. And it turned out that the number of civilizations, N civilizations, was somewhere between 0 and tens of millions. So not all that informative, right? But Frank Drake and others felt it was still worth listening. It actually hasn't been until the last couple of years that NASA agreed with that and started to fund some limited SETI research. All SETI research before then has actually been privately funded. So then the next question was, how do we look for exoplanets? Right, so how do we discover which stars have exoplanets? It turns out that we don't actually, for the most part, for most stars, we're not able to actually see the planets themselves. Instead, we only see the star. And so we have to be a little clever and use our knowledge of physics and how the universe works in order to identify stars, or identify planets, pardon me. So one of the first and most obvious ways is what's called the transit method. And with transits, some light from the star will occasionally be blocked by their planets. And in this animation, you can see the little planet transiting the star, and as it does so, the light from the star dims very slightly. And from that, we can infer the radius of the planet because we have the relative ratio between the size of the planet and the size of the star. However, although this graph looks nice and easy to read, it turns out that the amount of dimming that a typical planet would make as it passes in front of its star is equivalent to about the amount of dimming you'd expect a gnat to make as it crossed in front of a headlight if you were standing a few miles away. Right? So it's a very small amount of dimming. Likewise, with that, you don't know when the gnat is going to cross, right? And so you'd have to look all the time. And from the ground, this turns out to be a very hard problem, right? We have day and night, so at least half the time we're not going to be looking. We have clouds, weather. Half the year we're not able to see a particular star. So the possibility didn't seem all that great. But we can build spacecraft now. And starting in the early 2000s or mid 2000s, we started launching a series of spacecraft. The one that you may have heard the most about is Kepler, launched by NASA in 2010. Right about the time that I was starting grad school. And so that's why I was involved in making the Planet Hunters website. And the Kepler spacecraft was in an Earth-trailing orbit. It was able to look at the same patch of sky 24/7 for 4 years until several of its gyroscopes had failed and it could no longer point in a steady direction. But during that time, it was able to look at 150,000 stars every day, all day. And that was good because one of the things I forgot to mention is that we only expect about 1% of the star systems. If every star had a planet, only about 1% of them are going to be oriented such that we'll be able to see the planet transit in front of the star. And so one additional bit to that is the farther away a planet is from its star, so Jupiter's much further away than we are, the less likely it is to be transiting, right? Any small difference is going to put it out of our line of sight. And so it turns out that transits are great because we can look at many stars at once, but we only see some of the planets. So the other primary method relies on the fact that planets don't actually orbit stars. The Earth doesn't orbit the sun. Instead, the Earth and the sun orbit the common center of mass between the two. And you can think of a center of mass as two people on a teeter-totter, a child and an adult. The adult is going to have to sit near the fulcrum of the teeter-totter and the child way out on the end in order to balance, right? And so the sun, being about 1 million times more massive than the Earth, is pretty much sitting on the fulcrum, whereas the Earth is, 8 light minutes away, or 150 million kilometers. And so as the Earth goes around that center of mass, so does the sun in the same year, always staying opposite that point. If you're looking at it from the side, like we do in this animation, then you can sometimes see the sun moving toward you and sometimes moving away from you. And with that, you could then figure out that there was a planet tugging on the star, making it do that. If there was no planet, it wouldn't be wobbling, right? And so what we need then is some way to measure that. And you've probably all heard of the Doppler effect, or at least witnessed the Doppler effect. If you have a siren coming towards you, the sound appears higher pitched than when it's moving away from you. The same thing happens with light. So as a light source is moving towards you, the frequencies are shifted to higher frequencies or bluer wavelengths. And when the light source is moving away from you, the light is shifted to redder wavelengths or lower frequencies. And so we can use this effect and watch a spectrum to see the light shifted back and forth and measure the velocity. And so over the last 30 years, those 5,600 or whatever it was, stars or new planets have been detected, 4,200 of them by the transit method, and another 1,100 of them by radial velocities. I mentioned that transits give us radius, and radial velocities give us mass, or mass modulo the angle at which we're seeing the system. There are other methods, like astrometry uses the two-dimensional position on the sky, and direct imaging is only recently become relatively successful. We're able to, particularly for young planets that actually have some residual heat, we're actually able to identify the planets directly by both the reflected light from the star and the residual heat from the planet. But you can see that the majority of the planets we've detected with transits and radial velocities. So that brings us to the next part then, in that we asked how we look for planets, and I've given you some methods here, but we also had some expectations, right? We had one solar system to go on, ours. I mentioned that it had a bunch of planets on widely separated orbits, but this is kind of the standard picture we all see in books and things, right? The planets look all roughly the same size with some small variation, and they're all packed close together. But in reality, this is a really bad image, and it all gets stuck in our brains. And so I want to take a little while to pick apart what we actually have. So these are only the 4 inner planets, and this is the solar system to scale. I couldn't put the rest on there because they wouldn't fit on the screen, or you wouldn't see the planets. And so here, the little tiny dots going around are to scale, and the green area is the habitable zone. So you can see that Earth here is just on the edge of the habitable zone. If we were any closer, it would be a little too hot. Our atmosphere would start to vaporize. You can also see that Mars out here on the outer orbit actually is very close to the outer edge of the habitable zone. So this has led us to thinking, well, you know, early on, maybe Venus would have been in the habitable zone and Earth a little further out. So maybe there's between 1 and 3 planets that actually hit the habitable zone at some point in our lifetime, right? So this gives us then a sense of scale, at least of the inner solar system, but it's hard from these little dots to see the scale of the planets. So here's one where the distances are no longer correct anymore, but at least the scale of the planets in relation to one another is. And so we can see we have the small planets inside. Mercury is really tiny. Jupiter, it's really only 12 times the diameter of the Earth's diameter, although it's more than 300 times its mass. And so you can see that we have a range of sizes and a grouping where we have the small things interior to the big things, right? And this is kind of what our expectations were in looking out at other stars. And so of these 6,000-ish planets, sorry, I can't say 6,000-ish, what have we found, right? What are those planets like? The very first planet, well, the third, so we found 2 planets around a dead star called a pulsar. but we really count this 1995 discovery around a main sequence star like our sun, a star in its prime, as the first planet discovery. It was 51 Pegasus was the name of the star, so the planet's name was B. 51 Pegasus B. Astronomers are really great with their naming. It was not what we expected at all. It's about half the mass of Jupiter, so it's a big planet. So where would we expect it? Further out. Anyone know what the orbit of 51 Pegasus B is? What its year is? How long its year is? So our year, of course, is 365 and a quarter days. 51 Peg B orbits in 4 and a quarter days. And a little surprising, or is a lot surprising, because we don't think that gas giant planets like Jupiter can form 4 days away from their star. Right? So we had to start looking into our theories about planet formation and migration to try and figure out what was going on. And it turns out that in 2010, when we started collecting all of these planets rapidly using Kepler, they were weird as well. So the weirdness didn't stop with the first planet. Right? So here in dashed lines, I've again got the orbits of the solar system planets, and in the solid lines, at the same exact scale, I have the orbits of planets around other stars. And the planets aren't to scale with the orbits, but they're all to scale with one another, so that you can get an idea of the kind of systems that we're seeing, and the speeds. You'll see the solar system planet speeds compared to the speeds of the others. And things are a little odd, right? Everything, all of the planets that we found between 2011 and 2013 would have fit inside the solar system on their orbits, right? So the planets that we were finding were nothing like we expected. And so if that was what we were finding with transits, then what were we finding with radial velocities, right? Were we finding anything more like what we expected? So this isn't as great animation. Instead, I've got a plot for you, I'm sorry, but on the vertical axis, we have the signal strength, the velocity at which the star is moving because of its planet tugging on it. And along the bottom, I have the year of discovery. So if you look at these points, you'll see though over there in 1995, when we found 51 Peg B, it had a radial velocity signal of about 60 or 70 meters per second. So it was really tugging around on the star. For reference, this is the signal that Jupiter would impart on the sun, about 12 meters per second. And you can see that by the year 2000, we could find Jupiter-like planets. Right? A few years later, in 2005, we had the ability to find Saturn-like planets, where the signal could be as low as only a few meters per second. But then you notice something odd in that we kind of stall around 1 meter per second. We get lucky a few times, but pretty much a meter per second seems to be our limit. But this is where the Earth signal is. It's at 9.5 centimeters per second. And so we're able to find Jupiter and Saturn, but what about Neptune and Uranus? They're much further out. The further away you go, the smaller the signal. And so, or rather, the longer you're going to have to wait for that signal. What have we found then in those almost 6,000 planets? It turns out that mostly we found gas giant planets like Jupiter, almost 2,000 of them. We found 460 Neptunes, so Neptune is about 20 times the mass of the Earth, around 4 times the radius. We found almost 500 what I'm calling terrestrial planets, so Earth-ish in size, a little bigger, a little smaller. But weirdly, we found about 3,000 planets between the size of Earth and Neptune. Now, if you remember back to that image I showed of the solar system, there was nothing in the solar system between Earth and Neptune. That's why I'm using them as references, right? We've got one that's 20 times the mass of the other with nothing in between. And yet we found 3,000 planets that were just somewhere in the middle. We alternately call them super-Earths or sub-Neptunes, depending on which one they're closer to. But there's a whole range of sizes. And so everything about the planets that we found so far didn't meet our initial expectations. And so in 2016, when I was finishing up grad school, my advisor at the time, Dr. Deborah Fisher, who I noticed a little earlier is in the slideshow on the wall out here, looking at a spectrum of a planet or a star. So I was on her team that helped develop a new spectrograph to look at this region that I'm showing. So, sorry, these two plots. On the left, I've got planets discovered by radial velocity around stars that are kind of sun-like. And so I've got the mass, and on the bottom, the orbital period. And this one on the right is transiting planets, planets detected via transit, with the radius on the left and the orbital period on the horizontal axis. And you can see, if we look at the transiting planets, that there's plenty of these small planets, right? We found plenty that are the radius of Earth or smaller even. But this vertical line that I've drawn, that's an orbit of only 40 days. So most of those transiting planets actually orbiting in less than 40 days around a sun-like star. So they're just really hot planets, even the small ones. But if you look over here at the radial velocity planets, there aren't any that are smaller than Earth, and not even very many close in size to Earth, right? So where'd they go? Why haven't we found those? And so that motivated us, along with several other groups, to build a new spectrograph that could actually detect much smaller signals. We wouldn't be stopped at this 1 meter per second, and we could start looking for the planets that we know exist over here, but also looking for these planets over here. Here's where the Earth is in both images, and we haven't found anything even remotely like them. So what we'd like to do is start pushing down toward those smaller, longer period planets. So we built a new spectrograph called Express. It's on the Lowell Discovery Telescope south of Flagstaff, Arizona. And that's a medium-sized research telescope. It's 4.3 meters in diameter, the primary mirror. For reference, the 3-meter telescope across the road is, well, 3 meters. The 120-inch telescope across the road is 3 meters. It's a very high-resolution spectrograph. If you know anything about spectrographs, there's the number there, but take my word for it, it's relatively high resolution. And it uses a relatively new device called the laser frequency comb. That won the Nobel Prize a few years ago. And we've been on Sky since January of 2018. At the time, we were one of 2 spectrographs in the world that were able to get 30 centimeters per second single measurement precision, so we could now push that well below that 1 meter per second level. And now there are 3 others, so there's about 5 spectrographs in the world capable of doing these kinds of measurements. Some of the challenges in trying to push all the way down to Earth-sized planets are measuring these accurate pixel locations and also dealing with temperature, pressure, and vibration of the spectrograph itself. And so what I'm showing in the background of this slide is actually the laser frequency comb, which helps us both measure the pixel locations that we need to figure out when the wavelengths shift, and it also helps us track the changes in temperature, pressure, and vibration. But we also, this is an image of the spectrograph as we were putting it together along with Ryan for scale, graduate student at the time. And you notice that the spectrograph sits on these vibration damping springs in this vacuum chamber that we then closed, sealed, pumped down in a vacuum, and coated in insulation in this temperature controlled room. That it sits on vibration damping springs on its own pier in the telescope room, in the spectrograph room, separate from the observatory. So we're really trying to minimize anything that can affect our measurements. However, we still have astrophysical challenges to deal with, and those are probably much more complex. So we have the fact that we're spinning on our axis and rotating around the sun. That's annoying. It would be really great if we could stop. We have water and oxygen lines in our atmosphere. We point at different angles, so there's more or less atmosphere to deal with. We have the boiling motion of the star's atmosphere and what I'm calling weather. We call it stellar activity, which you can see here in the image. All of that messes with our measurements. And so getting down to this 10 centimeter per second level is very hard. And along with the spectrograph, we started the program we call the 100 Earth Survey that's been observing since February of 2019 at relatively high cadence. So nights are costly, so we get as many as we can. We get between 15 and 25 a year, a semester. And during those semesters, we divide those nights into quarter nights. So we have between 60 and 100 nights per semester, or a couple hundred nights a year, in order to try and look at these stars, these 60 stars, at our 30 centimeter per second precision, or even on a given night, we could take multiple exposures to get us down to 20 centimeters per second precision. Still not quite down to Earth, but we're getting down to these small planets, and these planets on longer orbits, right? And so last year, we published the first new detection, and this was a really fun star to look at. This star had the 7th planet ever detected back in 1997, Rho Corona Borealis b. It's this one here, and that's a Jupiter-sized planet on a 40-day orbit. Planet C was found only in 2016, so almost 20 years later. It's 30 Earth masses, so about 1.5 times the size of Neptune, and it's on a 100-day orbit, or 102-day orbit. But that's all that people had found. And when we looked, we found those pretty easily. If you look at the red points, they match the blue line. The blue line is our model. The red points are the averaged data. So that's pretty good. But we also found a 20 Earth mass planet out at a 280-day orbit. So now we're getting into that region that we've been having trouble finding things in. And finally, we have this 4 Earth mass, or 3.7 Earth mass planet on a 13-day orbit. So this is one of those small planets that's been hard to detect with radial velocity. So we're starting to be able to finally find both these close-in small planets that were missing from radial velocity and the longer period medium-sized planets that were missing from both radial velocity and transit. And so we can start to build up a better picture of what really is out there rather than the weird things that we've been able to find up until now. So I've talked about finding individual planets. This is a system, but I really started this by asking about that we haven't found anything like the solar system. So it would be helpful to then look at systems of planets. And so I've just collected a couple. These are all of the planetary systems with measured masses for all of the planets, with 4 or more planets, with none of them beyond 100 days. So all of these planets orbit in less than 100 days. Do you notice anything odd about these? The dots are all to scale with one another, and the orbits are all to scale. Very uniform, right? The dots in any given system are all about the same size, and the spacing between them is pretty regular. And we call this the peas in the pod. That these systems end up looking really uniform. And that was really odd. But you'll also notice the names of a lot of these systems. Kepler, K2, the TOIs is from the TESS mission. So these are all transiting systems, the ones that we found via transit. And I didn't choose them that way. It just, when you look for 4 or more longer than 100 days, then that's how it comes out. If you look at, if you allow that to expand to beyond 100 days, then this is what you find with transits. And some of those, they still look the same, right? We've still got these very regular spacings, everything around the same size, but we've now got some that aren't quite the same. This one, 55 Cancri, is interesting because we've got some big ones both inside and outside. The next one here, we've got, again, here we've got 2 little planets bookending some big planets. Here, it looks like solar system-like, right? We've got some small ones inside and a big one outside. But then you look at the small ones scale here, and you realize, oh, those are 3 Neptunes on short orbits with a big Jupiter one outside. So that's not either. And finally, Rho Corona Borealis here, where we found the planet. That one's got a small one inside, 2 Neptune ones outside, and Jupiter in the middle. That also isn't really solar system-like. But at least we're now seeing a variety of system architectures and not just these peas in a pod. So coming back to this statement and question, I'm afraid I don't have an answer. I think that we're just now getting to the point where we can identify solar systems that look kind of like ours and planets that look like those in the solar system. And so it's my that there's probably lots of such systems out there, systems that look like ours, but we just haven't been able to see them yet. And we have a lot of data to now start to look at that. In the past 30 years, we've come a long way, and certainly since 1961, we've come a long way. So I thought I'd look at the numbers in the Drake equation again. And this is actually something I have my students do in the exoplanets class I teach at the beginning of the semester and at the end of the semester as they learn more. And so we still know a few stars a year are born in the Milky Way, that now we know that this number is about 1, that almost every star has a planet. We still don't really know the number of habitable planets, but we're guessing from the solar system it's somewhere between 1 and 3. The fraction where life evolves, we don't know. Intelligent life, who knows? Communication, unknown. The time that they exist, unknown. And we've got exobiologists working on those problems. And when my students go through and they put in their numbers for this at the beginning and the end, they come up with a number somewhere between 0 and 10 million. So although we've made some progress, there's still a long way to go. So how common is the solar system? We don't know yet. But I think we're getting close, and stay tuned. So with that, I'll put up the Express 100 Earth's team that's actually doing all this work and take any questions. Thank you.
Why
Sure.
do you define the solar system as having rocky on the interior and gas on the outside? I mean, that's our example, but you seem to have fixated on that. You're unhappy that you have these mixtures.
So I'm not unhappy that we have the mixtures. It was just really odd to find the peas in the pod systems, where instead we had all the systems, all the planets being the same size, whether that was gaseous or rocky, although it tended to be rocky or Neptune-like. And I think that primarily the formation mechanism that we expected from the solar system, and we still largely think holds, is that when a planetary system is forming, the area near the star is hot. And so you wouldn't expect gaseous things to be able to form until the rocky things have formed. And further out, it's cooler. You expect ices to form, gases can accrete on the ices, and so you expect big planets outside. And we still largely think that's true, but now we think things can migrate around. And then you end up with those mixed systems that are also kind of interesting. That's a great question, though. Yeah.
Do you think you can actually improve the RV and the transient to find the solar systems you want, or limited by physics to the extent that you can find out that?
That's a great question. I put in a lot of grant proposals saying that I could do that. In fact, I just hired a postdoc whose sole job is to improve our 30 centimeter per second precision beyond 30 centimeters per second with the things that we already have. Because as I mentioned, our biggest impediment now is not our instrument, which can measure down to 20 centimeters per second, say. It's really the star. So I happen to be looking at very quiet stars, really well behaved. But we also have a few that are not so well behaved, and we don't do 30 centimeter per second precision. We do meter per second precision on those. And so I think that we can improve even the quiet ones by some complex machine learning and really digging into the data and figuring out what's there. Yeah.
Is there a way to know if there's water on those very far away planets?
That's a great question. One of my colleagues at San Francisco State actually doesn't work directly on exoplanets. She works on brown dwarfs, which are kind of an intermediate stage between a star and a planet. And she looks at brown dwarf atmospheres to try and study how we'll look at planet atmospheres. But a lot of her colleagues over here at NASA Ames, they actually are using the James Webb Space Telescope to look at the atmospheres of planets. And so we've actually measured the compositions of the atmospheres of some giant planets so far. Now, once you get down to smaller planets like the Earth, that becomes a much more challenging prospect. And so that's something that we're still working on.
The work at the Express team is Earth-based, right? So you have the influence of the atmosphere. Would you get significantly better results if it would be in space? I understand you still have the activity of the sun, the planet.
Yeah, so the only issue with going to space is the size of that. And what I'm not showing you is in the other room is the laser frequency comb that's a whole rack of equipment. So trying to get the precision that we need to make these small measurements because Earth still is only imparting a 9.5 centimeter per second signal. We need to miniaturize things in order to fit it in a spacecraft. But that's going to be ideal because cadence, like the weather is killing me. As climate change has really messed with our observing schedule. The telescope, when it went online in 2012, had a great sight, only about a quarter of a time where you weathered out. And last year, I think I lost half the nights. So.
Yeah, just a quick question. So when you were referring to Earth-like objects, like similar size Earth-like objects, was it related to the size of that sun in the solar system? Because it could be habitable if the sun is maybe 10 times bigger as compared to our sun.
Right, that's a great point. So the only stars that we're looking at in our survey are between about 65% the size of the sun to maybe 105% the size of the sun. So we're only looking at a very narrow range of stars. And so it still is true, and I kind of glossed over it in some of the plots, but the temperatures of the planets are actually colored. And so this is about the color that you want to see for something that's in the habitable zone of its star. But the only ones that are that color are giant planets so far. So, great question.
One more question, and then we'll move and be able to ask some more questions.
One question. So basically habitable zone. So how do you calculate it? Whether this is like a habitable zone.
So there are actually many definitions of a habitable zone, but the most basic is just the point at which a rocky planet could keep a liquid water on the surface. So you do that by, you know how much solar radiation is coming in or stellar radiation is coming in at that point. You know the mass of the planet, so you know the escape velocity of the particles coming off it. And so you can, between those two, you can calculate how much the atmosphere will be able to retain heat and give you liquid water on the surface. That's the basic definition of the habitable zone, but there are many factors that then go into it, including the fact that the star changes temperature as it ages, and that planets can migrate or be on elliptical orbits. And so there's several commonly accepted habitable zone definitions, but it's just kind of a rule of thumb. And really, we're only using it because we're the only life we know in the universe so far. And so our life is water and oxygen based, and we need to look for other planets that can have water and oxygen on them. And so that's what we're looking for. But we could be surprised again.